Hello, beautiful humans. Today we are going to talk about graphing logarithms. And first we need to review graphing exponential functions. So we're going to start there. And some of this actually might be new depending on how much you got through last year. So let me know if we need more on this. Okay, so we didn't really talk about exponential functions when we talked about all of the different functions because they kind of have a different rule. Every exponential function has a unique mother function, so to speak, because that base determines the shape of our function or a lot of features of our function, right? So if the base is 2 to the power of x, that's going to look slightly different than 5 to the power of x. So every mother function is unique to that exponential. All right, so we have it in the form of a times b, our base, to the power of x minus h plus k. All of those things, a, h, and k, do the same exact things to transform the function. So if we have 2 times 3 to the x minus 4 plus 5, that this would all be in parentheses, by the way. My computer was having parentheses issues. But what we would do is say, okay, that a value is 2, so it's going to stretch the function. Every output will double. My base is 3, so 3 to the power of x would be the mother function that we would base it off of. Then we would shift right 4 units because of that h value of positive 4, and we would shift up 5 units because we have a positive k value of 5. All right, so in order to do this, the best way to graph these is just to think about, okay, what would the very most basic version be? So the mother function of this given function would just be 2x. So we're going to create a table for 2 to the power of x and see what this is going to look like. So start with -2, -1, 0, 1, and 2, right? So if we take 2 to the power of -2, that's the same as 1 over 2 squared. Remember our negative exponent rules. So this is going to give us 1/4. This will give us 1/2. Anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. So that's the most basic version, 2 to the power of x. That's how I'd graph it, right? A couple things really important to point out. Where are the asymptotes on this? Well, this the mother would have an asymptote at y equals 0, right? Y equals 0, our horizontal line there. So this function has been shifted down 4. So our new asymptote is going to be at y equals -4. Okay, so if we were to graph the original would have an asymptote right here at y equals 0. And then we would go ahead and graph our -2 is barely up at all. -1 is 1/2. 0 gives us an output of 1, 1, 2, and over 2 up 4. So this is the graph of my most basic 2 to the power of x, the mother function of this exponential. All right, so we identify anchor points. The y-intercept is a key one. So in this case, our anchor point would be 0, 1. And then we also want to pick another point so we can really see this transformation. So I might pick the point 1, 2 as well, just another point to look at here. Okay, so now we need to apply our h and k transformations. So up here, we know that h is going to be -3 because we're shifting to the left 3, right? The value of x that would give us that 0. So we're going to shift to the left 3 because that h value is actually a -3. So we're going to go left. Oops, that's not what I meant to do. Let's get rid of that. We're going to go left 3, right? So that means we're going to subtract 3 from our x value. So we need to subtract 3 there and also on the other point that I'm going to look at. And then all of our y values are going to also subtract 4 because we have a -4k value here. So we're also going to subtract 4 from our y values. Okay, so the reason we're doing -3 is because of that h transformation. The reason we're doing -4 is because of our k transformation. So what we're doing is taking 2 points and applying the transformation to those 2 points. All right, so now our new points would be at -3, -3, right? 0 -3, and then 1 -4. And then our other point would be at -2, -2. All right, So we're going to do our new asymptote because I said that's a really important thing to identify. So we're going to shift it down 4, right? 4 below our original asymptote. We're going to go down 4 and draw our new asymptote. So we have a reference, right? And then we're going to graph our 2 anchor points so that we can see what our new graph is going to look like. So when we go -3, 1, 2, 3, we're going to go down 3, 1, 2, 3, boop. And then when we go -2, -2, there's another point. Okay, so again, we're looking for this graph to have shifted left 3 units and down 4 units. So what we did was take these 2 points here and we shifted both of them down 4 and left 3. And our new function is going to look like this. Okay, our new exponential function. And again, the more points you plot, the more accurate your graph is going to be. You absolutely must show me 2 points and your asymptote in order to get full credit on a graphing problem like this. All right, let's go to the U try. I've already set this one up so that for the sake of time, hopefully you tried it on your own first. All right, so we have a H transformation of +1 this time. We have a K transformation of +2. So again, we're going to start with our most basic version, 3 to the power of x, and create our table. Remember, when we raise something to a negative power, like -2, we have 3 to the -2. That's the same as 1/3 squared, remembering our negative exponent rules. So we get 1/9, and then 1/3, 1, 3, and 9. Okay, so when we graph that, again, our asymptote is at y = 0. Should have drawn that in. There you go. Asymptote is at y = 0 for this original, this mother function, right? And then we need to take our 2 points. Again, I chose our anchor point 0, 1, and then another point just 1, 3. You could pick any of the points. You just need to use 2 points to make sure you're showing the transformation. And then we're going to add 1 to all of our x's for that H transformation. We're going to add 2 to all of our y's for our K transformation. Again, our asymptote is also going to shift up to that K transformation, tells us where our new asymptote is. So we're going to shift up 2, and that will be our new asymptote. I graphed the original in black and our transformation in purple. So you can see we shifted up 2 and right 1, and that's what those points look like there. Hopefully that's making sense, and hopefully this is kind of a review. If not, let me know so that we can do more on this. All right, so how are we going to graph a logarithmic function? Well, the first thing we want to do is convert this to an exponential so that we can create a table, because we know how to do that for exponentials and we don't know how to do that for logarithms yet. So we're going to create a table using our exponential, which is our inverse function, right? So we know that inverses, we swap our x and our y. So we're going to do x equals log base 5 of y. And then we need to snail method, well, backward snail method. Here, let me write it this way so it looks normal. Log base 5 of y equals x, right? Normal snail method that way. That way we get 5 to the power of x. So the exponential inverse of our logarithm is 5 to the power of x. So we're going to go ahead and create a table for 5 to the power of x. And then we're going to use what we know about inverse functions to create a table for our logarithmic function. So 5 to the power of x is going to be x and y. So again, I would start with -2. Again, that's going to be 1/5 squared. So that'll give us 1/25. -1 would give us 1/5. 0 gives us 1. Anything to the power of 0 is 1. 1 is going to give us 5. 2 is going to give us 25. So that is our exponential function. Let's point out where the asymptote is. That's super important. So again, this is a parent function of an exponential. So the asymptote is simply at y = 0. All right, now we need to graph it. So let's go ahead and graph our exponential function. So at -2, we're barely off the line there, barely at all. -1, 1/5, still not much. 0, 1, 1, all the way up to 5. And then our next one's going to be off the graph, right? Because this is going to go pretty quickly. Okay, so there's our exponential function. Now remember that our inverse functions are always a reflection over the line y equals x. So the line y equals x looks like that. So when we reflect this, it should, or when we graph our logarithm, it should look like a reflection over that line. So that's going to be an important check for mental check for you. Okay, so if we have log base 5 of x, again, that's the inverse of the exponential 5 to the power of x. Well, what do we know about inverses? Well, the x and y outputs just switch, or the x and y's switch, right? Our inputs and outputs swap. So all we're going to do is take our table and do the inverse. So we're going to have 1 over 25 would give me an output of -2. 1 over 5 would give me an output of -1. 1 would give me 0. 5 would give me 1. And 25 would give me 2. Okay, so that's our logarithmic function. So now we just need to graph those points. Again, we're going to do our mental check of making sure it does in fact look like a reflection over that line. So now I'm going barely at all to the right, and I'm going to go down 2, and then barely at all to the right still, and down 1, but slightly further that way, right? And then over 1, 0, over 5, up 1, and then the next one's going to be off the graph, okay? All right, now, if you think about inverses, so what we had was a horizontal asymptote, right? We had this horizontal asymptote here, and then we took the inverse. When you take the inverse, the asymptote is going to switch to a vertical asymptote. So now we have our logarithmic function has a vertical asymptote. Boop, boop, boop. Vertical asymptote. So this vertical asymptote is going to be at x equals 0. So we have an x equals 0 vertical asymptote for our logarithmic function. We have y equals 0 for our horizontal asymptote on our exponential function. So these asymptotes are going to also switch, right? So logarithmic are going to have a vertical asymptote. Exponential will have a horizontal asymptote. On the Delta Math, when you're doing the practice for this, it's going to have you describe logarithmic functions. And one of the things it's going to talk about is as x goes to, so when we're talking about the end behavior here, x is going to approach 0, right? Because we can't go any further than that vertical asymptote. In Delta Math, they're going to use notation that'll be more common for pre-calc. So they're going to say as x approaches 0 from the right. Okay, so basically we're saying we're going to come in from the right, and we're heading toward that vertical asymptote at x equals 0, right? So we're going to approach that asymptote from the right, though, because from the left, there's nothing there. That'll become important in pre-calc in the future. So just heads up when you're describing these logarithmic functions in Delta Math. All right, here's a you try. I've already done it for you. So again, we're going to start by identifying our exponential. So we'd swap our x and our y. We'd use our snail method. We get 2 to the power of x equals y. So I'm going to first create a table for 2 to the power of x. There you go, right there. Then I'm just going to swap my x and y values. That's going to be my inverse, which is my logarithmic. So remember, key concept here is that exponentials and logarithms are inverses of each other. So when we create our exponential function, we can just swap our x and y values, and then we have our logarithmic function. Again, this should look like a reflection over the line y equals x, which it does, so that's fantastic. When we have our exponential function, we have a horizontal asymptote at y equals 0. When we switch to our logarithmic, again, that's going to switch to become a vertical asymptote at x equals 0. So what was a horizontal asymptote is now a vertical asymptote for our logarithmic function. All right, next example, we have log base 1/3 to the power of x. Okay, so again, we're going to swap our x and y. We're going to say log of 1/3 of y equals x. So 1/3 to the power of x equals y is my inverse exponential function. So let's do 1/3 to the power of x. Notice this is going to be exponential decay. The last couple we have done have been exponential growth. So anytime your base is a whole number, it's going to be growth. Anytime your base is a fraction less than 1, it's going to be decay. So this is going to be shaped differently, right? We're going to decay over time instead of growing over time. So just something to keep in mind. So when we create our table for this, so when we plug in -2, 1/3 to the power of -2, we're going to flip that fraction. It's going to be 3 to the power of +2. So this is going to be 9. -1 is going to be 3 to the power of +1. So 3. Anything to the power of 0 is 1. +1 is just going to give me 1/3. When I square 1/3, square the top is still 1. Square the denominator, we get 9. So we get 1/9. You should be recognizing patterns here for these basic exponential and logarithmic functions, how we're getting these outputs. Okay, so then if we want to create the logarithmic, we're going to swap our inputs and outputs because that's what an inverse is. So what was an output of 9 is now going to be our input of 9, which will give me an output of -2. What was an output of 3 will be my new input and give me an output of -1, 1, 0, 1/3, 1, 1/9, 2. All right, so let's go ahead and graph both of these. Let's start with our asymptote. So we know we're going to have a horizontal asymptote at y equals 0 for our exponential function. We're going to have a vertical asymptote at x equals 0 for my logarithmic function. Okay, and then for my exponential, I'll do that in black. So we're going to go -2 is up to 9. And then -1 goes to 3. And then 0, 1. And then 1, barely up 1/3. And then 1/9, even closer to my asymptote. And again, we have exponential decay. I also like to put in my line y equals x so that I can do a check here and make sure that my logarithmic function does in fact look like a reflection over the line y equals x, because that is what an inverse is, so that should be the case. And now we're going to graph our points. So we're going to go over 9 in the positive direction and down 1. And then we're going to go over 3, down 2. And then we're going to go over 1, not down at all. And then we're going to go 1/3, up 1. 1/3 right there, up 1. And then we're going to go 1/9, right, very, 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 very close, up 2. All right, so now why did I only go down 1 on my, that point did not look correct over here. Let's try that again. -9 should be down 2, and 3 should be down 1. I messed up both those points. Try again. Okay, again, having these values in here is going to help you catch mistakes because that did not look right to me. So I needed to fix it. Again, I know I'm going to approach this vertical asymptote here, and I'm going to go that way. Again, because this one is decay, these inverses look different than they did in this last example, right? A little easier to see the inverse on this one, but these are a reflection over that line y equals x. If you could smush them, and if my graphs were a little better, it'd be a little more obvious. So the more accurate you can graph these, the better. All right. Last but not least, we have another you try that hopefully you are trying. You already tried. So if you have log with no base, remember that means log base 10. When we convert this to the exponential, we get 10 to the power of x equals y. We're going to create our table for our 10 to the power of x, our exponential function, and we're going to graph that. This one gets big really, really fast. Notice I changed the scale on my graph because it gets big so fast. 10 to the power of something is going to grow rapidly. The logarithmic is just the inverse, so we're going to swap those values. Again, should look like a reflection over the line y equals x, which it does. So we're looking good here. Hopefully this makes sense to you. We're going to do more graphing next week, add some of those transformations that we talked about with the exponentials. So make sure you ask me questions if you have any questions on this. Have a wonderful rest of your day.